we can start. So first of all, hello everyone, and welcome to the SLT, the SIG SLT seminar. So today we are very happy and honored to have here Professor Shinji Watanabe. And Shinji is an associate professor at Carnegie Mellon University in Pittsburgh, yes. And is a huge experience in speech recognition and speech translation. And his group has plenty of paper at the top conference, and is also the developer of the SPNet toolkit, which is one of the most used toolkit for speech recognition and speech translation. Today, we will talk about controllable and explainable end-to-end speech translation. So thanks a lot for being here and accepting our invitation, and I leave you the floor. Usually, as you prefer, Shinji, you can have a question in the middle or at the end. Please let us know what you prefer, and it's perfectly fine, both solutions.
Okay, sounds good.
Yeah.
Thank you, Marco. Thank you, Marco, for the great organization, and I'm very honored to be here and introduce some of our recent activities. And the title is, as Marco already mentioned, Controllable and Explainable end-to-end speech translation. So I first would like to mention about the black box nature of the end-to-end neural network, and specifically for the speech translation cases. For example, a human can, human sometimes, of course, has some mistakes, but still mostly human is great in terms of they can understand the sound and translate, and then they can actually produce the translation. While the machine, we still have some issues. We still cannot fully kind of solve our problems. And in these cases, there is one mistakes. And then let's try to think about what went wrong and how can it be fixed. So one possible kind of a reason of this, the mistake would be that, as you see that one token, one word in German side is missing. This is short, actually. And then to avoid it, we may try to generating the translation that will be the sufficient the length. That is kind of one of the possible reason that this translation might not working well. And the other possibility and how to come up with is that like human, first we try to recognize what was said, which correspond to the ASR, and then translate it to the target languages. And then we may actually improve the performance and so on, because we now know that this machine has intermediate explicit representation based on the source, the language. But this is not still enough. For example, frankly, for me, I still don't know why this error happens, because I know English, but I don't know the German. So how to kind of analyze what's happening in this computer machine would be that one possibility is to find some kind of correspondence of the word of the source language and the corresponding the target languages. If we know these kind of situations, we may actually understand why this the machine misrecognize this mistranslate this sentence and so on. So these three are today's actually main talk. So today's talk, I will talk about mostly two papers, which is the previous the IWSLT submission for dialect speech translation system, and this actually covered two of our problems. Controlling speech translation output length via joint CTC attention. And the second part is controlling the explaining speech translation via searchable ASR intermediates. And the third part is actually covered by our recent work, which we actually published the archive very recently. This is explainable speech translation via word level alignment. And today, I will talk about this topic one by one. By the way, I forgot to mention, but anyway, these are the slides are mostly done by made by my student Brian Yan, and this work actually done by the Brian and a lot of my kind of colleagues are listed here in the these papers. Okay, let's first focus on the first topic, controlling the output length. This is actually quite an important problem. For example, what is good translation? Of course, it should have a correct meaning. But at the same time, it should also have a correct length. And actually, one of the IWSLT tasks, isometric speech translation for subtitling, is also tackling this kind of problem and so on. And why the length is so important? Actually, it's depend on the current our technology, autoregressive decoder. It generally does not have a robust end detection. So that we actually have to making a tuning of penalty, bonus, or hyperparameter, so that we can actually making the translation to be correct length. And then this is actually one of the example. If, for example, we set the length penalty very different, and then actually performance is quite significantly degraded. So this part is very, very difficult problem in general. And we actually faced on this issue in the last year. So last year, we actually submitted our IWSLT system in offline the task, and we tune our system, especially for the length part. And then in the test set, development set, we actually got a significant result. And we are very sure that we got a very good result. But it turns out that in the real evaluation, actually our performance is not very good. This is mostly because the annotation guideline pipeline is changed and the reference length was actually changed, which is actually happens. And I would say that it is our fault that we actually highly tune length depending on our kind of development set. That is a quite a difficult problem. And I believe people here also have this kind of something similar experience or try to solve it in sophisticated manner. So we want to solve this problem and we are thinking about it. And then it seems like we had the same experience before. Oh, yes. We actually had the same problem when we first applied attention mechanism to speech recognition. And actually, our group solved this problem by using the joint CTC attention modeling. So joint CTC attention modeling is first using the attention-based encoder-decoder as a main ASR systems. However, we also attach CTC as a regularization of the learning, and also we utilize CTC output during the beam search. As you know, CTC has a monotonic behavior since this is based on the hard alignment, so that we actually can easily eliminate this the non-monotonic behavior by combining CTC. So this is still ASR result. But anyway, for example, first line, first row is the pure attention-based model. And then it's often the attention, source target attention, the weight is corrupted. This is actually the attention, the monotonic behavior is corrupted. While a joint CTC attention model can actually make a beautiful the monotonic constraint thanks to the CTC. And this means that we can also correctly get to the end of the sentence and correctly control the length based on the CTC. Okay, so then our solution is simple. Let's try to use CTC in addition to the attention-based speech translation system. How to do it? We attach a CTC here, like similar to the joint CTC attention in ASR. However, there is one discussion. Wait, speech translation does not have a monotonic behavior since it's also including a deordering. CTC is monotonic, so the model cannot be applied. This might be true. However, we found that, and the other group also found that actually recent techniques, especially self-attention itself, has a reordering functions. So by using the self-attention, we could actually mitigate the reordering issue so that which already happens in the self-attention side in the encoder. And the decoder part is actually almost monotonic. So in this example, left side is actually having some non-monotonic issues. But with the self-attention and our careful condition, we actually can make the source target attention to be almost monotonic so that we can safely apply CTC. Probably this is before attention, the BLSTM, this kind of the problem might exist. But based on the self-attention, we can actually ask encoder part to do the reordering. And then target, the source target part can just could solve the monotonic the translation problem. And we actually also found that by using our technique, we actually can improve the monotonicity, and then we can actually show that the joint CTC attention can be safely applied to our problem. Okay, let's then apply it to our speech translation problem. The first part is a kind of analysis of whether this CTC approach can make our alignment problem, length control problem to be robust. So this is the result. So red line is the conventional end-to-end system. And as you see, if we using the length penalty to be larger, and then our kind of the performance of the blue start to be degraded. Again, this is, as I mentioned before, the length control of attention is not so straightforward. But by using the CTC, by combining it with the CTC, we can actually easily control the length, and actually the method becomes quite robust to the length. So this is the one good thing that we can actually control the length based on the CTC. And then let's also check the actual performance. So this is our result in the several kind of benchmark. And as you can see that by using the CTC attention, not only we just can get the controlled the length, but we can also got the improvement, possibly due to the regular the attention map that we also obtained in the ASR cases. So by using this CTC attention, we can actually find a quite nice improvement in the speech translation. By the way, same concept we can also apply to the machine translation. And then we can get an improvement. So now that we can revisit our problem, our technique with this CTC attention. And this year, we actually attended the dialect speech translation task in the IWSLT'. And this test 1 is corresponding to the development set, and test 2 is a hidden set. And as you can see that now our tuning effort is actually reflected to our kind of evaluation set safely. We have actually quite a high correlation, and we can actually solve the problem of the overtuning comes from the length. And we can finally get a very good, nice result in this task. So this is the first part of my talk, and I will move to the second part, which is the searchable ASR intermediates. This is actually a little bit old task, the method we proposed 1 year and a half ago, but we actually found that this is still very powerful, and our IWSLT submission was actually performed very good thanks to this. So I would like to actually reintroduce this method, if assuming that not so many people knowing this technique. So anyway, this the searchable intermediate technique is actually try to imitate the cascade system. Many of the speech translation system currently, to get the best performance, most of people are actually using the cascade system than end-to-end system. The reason is because by using the cascade system, we can, for example, improve the ASR system by using the ASR data or a lot of ASR techniques. And then the machine translation is just to get the benefit of the better speech recognition result. And then our approach is try to imitate this approach by using an end-to-end neural network manner. Just I want to note that this part is actually transcription. So we get the argmax. So there are a lot of techniques to make this to be differentiable, but straightforwardly, it is not easy. Instead, we actually passing the information of the decoder hidden state to the machine translation. I will explain it a bit more. So this is a more like the definition of the ASR decoder state. And I would like to mention why this ASR decoder state is important than transcription in our cases. So first, again, this is ASR, not speech translation. But anyway, ASR problem with is to try to get the best the speech recognition result given the speech features. And attention-based encoder decoder actually factorizing this problem to estimating the token given the hidden state based on the decoder state. And then decoder state actually has a lot of information. Decoder state has a previously estimated decoder state conditioned on the previously the estimated decoder state and previously obtained token, and the observation information, which is actually encoded as an encoder. And since this is the continuous value, this ASR decoder state is actually differentiable. So if we pass this information to the MT, actually it can make a kind of a single computational graph easily. And note that if we do that in the transcription cases, since we have argmax, this kind of treatment is a little bit tricky. Second, this decoder state is actually conditioned on the previous token. And during inference, this is actually obtained by search or fusion. Like, for example, the famous example would be a beam search with language model. This is a kind of a search and fusion. This actually defines the estimated previous token. And this the hidden state means that we incorporate this kind of a search information in the hidden state, so that we call this the hidden state passing to the machine translation. We specifically call it searchable intermediate. And also note that we can also passing the encoder state like this approaches. This is more like a classically people are doing. Can we make this to be searchable? It is possible, but it is not straightforward because encoder generally doesn't have a condition on the previous token, so that it's not easy to incorporate the search result. So this is actually our kind of the high-level concept. Let's try to use this ASR hidden searchable intermediate for our speech translation. So actually, this is our kind of entire system. We have a speech encoder, we have an ASR decoder, we have a speech translation, but it's almost corresponding to the machine translation encoder and the speech translation decoder. And then to connect this approach with the ASR hidden intermediate states, we actually having this kind of arrow. Here, we passing the encoder, the ASR decoder state. This actually can providing the search information. Okay, first check some really this kind of search information is helpful. For example, the experiment is showing that by controlling the beam search and so on, beam search parameter and so on, we control the ASR result in here. And then corresponding the intermediate hidden state can also be changed. And as you can see that if we have a better word error rate, if we get the better search result, that's the corresponding decoder actually improve the following speech translation result. This is obvious in the cascade system, but in our system, we can actually realize it by using this dual decoder system. Okay, then let's try to find how to improve the better ASR part. Then we can naturally improve the speech translation performance. So the first strategy is, as I mentioned, let's try to put our kind of ASR effort. In ASR, we can also use language model or even CTC that I mentioned before. Joint CTC attention can also be incorporated during the decoding here. And then we could get the better ASR performance, and hopefully that will also get a better speech translation performance. The second strategy is also classic. To improve the ASR part, we just try to use the raw bar, and then getting the better the ASR the result which corresponding to get better ASR the intermediates, so that hopefully we can also get a better result in the speech translation. So this is actually one of the most significant gain we obtained in the IWSLT 2022 Dialect task. So by using the strategy 1, which is combining the language model CTC during the search in the middle, we actually can get the better performance in our speech translation system. And the same happens to the rover system by using the rover to get a better ASR hypothesis. And then again, our the ASR decoder hidden state becomes better search result. And then these searchable intermediates improve the performance a lot. And this is similar to the performance gain we obtain by using the cascade system. Okay, so the last part of my talk is a little bit brand new result. This is try to improve the explainability of speech translation via word level ASR alignments. So the first, let's try to define the explainability in my cases, in our kind of other cases. For example, currently, actually many of the speech translation, end-to-end speech translation, also output the ASR result and the corresponding translation result. And this one is actually a little bit more structured. we can have our ASR result and the corresponding the translation, but we also keeping the word alignment information. And the question is, which one is more explainable? It is very obvious that this one is more explainable, right? So our target is try to kind of realize this explainable speech translation end-to-end system by using the word level alignment, the result. Okay, so I will explain this method one by one. We call this approach align right and reorder. So again, our goal is not just getting the speech translation result or supplemental ASR result. We try to get the result of this kind of structured form. How to do it? Yes, let's try to make it serialized by using alignment so that we can make this problem to be still sequence to sequence problem of the speech input to this kind of a tuple representation of the sequence. After we get this the tuple representation, how to get the translation result? We first extract the corresponding the target languages. However, everyone noticed that this is actually tied with the original source word, so the order is actually not correct. However, we actually also keeping the order information in the tuple. So that last step is to reorder this translation result so that we can finally get the speech translation result and the corresponding the speech the recognition result. So this is our kind of a concept. And this has actually two interesting merit. One is, yes, explainable. Actually, it is easy to analyze what's happened because not only we have an ASR result, we also have a corresponding the token, the target token result, so that we can easily analyze what's happening. And another interesting benefit is that this result is incrementally generated so that we can make it streamable. We can just get the intermediate result of the ASR and the corresponding translation result. And then once we have a position information, we can just reorder on the fly so that we can actually make this the speech translation to be easily streamable. Okay, the question is how to prepare this serialized representation. And we actually consider the first solution, which is just using the absolute position. We using the statistical aligner, and then we get this kind of alignment information. And then we have our word, and then the corresponding source word, and the corresponding target word, and we also inserted the position. And in these cases, for example, this one is first, this one comes from the last. So it's that has a position 3, 1, 2, and so on. This approach, we call it the absolute position-based operation sequence. However, this approach actually has a lot of limitation. Especially this is absolute number is quite annoying if we consider the very long sequence. Because in the test cases, we may not know the larger number than what we saw in the training data and so on. Also, when we start using it for the streaming cases, we cannot know the future position of this token. So this absolute approach has some kind of an issue. And then the second approach we came up with the relative shift. We actually are using the operation the sequence based on the shifting right head operations, which is originally proposed in the machine translation study. And we actually are inserting this position information, relative position information, instead of the absolute information. So the tuple becomes like this: source word, relative position, and target word, and so on. And then by using this kind of preparing this kind of tuple information, we can make this the approach to be working. Okay, so after we prepare this data, actually this problem is very easy. Just throw it to the existing end-to-end speech translation system. What we did was we only changed the data preparation part. Same for the inference. We just throw it to our existing beam search algorithm. And then, as I mentioned before, we just extract the translation result with reordering. So I will show you the kind of our kind of the video. This is a kind of the simulation of our result, not real time, but we actually also have a streaming result the blue score later. But anyway, I will show you the video of how it works. There is no audio. So this first line is actual beam search result. And then second line is we just extracting the ASR result. And then third approach is translation. As you can see that order is often changing. Maybe I can play it again. Okay, so this is a kind of our behavior. So now I just want to move to the result. So actually this the operation sequence generation is working quite well. This is the normal direct speech translation. And the second bar is absolute position-based approaches. It's not very bad, by the way, actually. It's slightly degraded performance, but still kind of the working as we expected. And the operation sequence based on the shift, the relative shift approach is actually doesn't degrade the performance, but still getting the explainability and streamable the result. This is the offline result, and this right side is actually streamable, streaming result. Okay, so this is the end of my talk. So I explaining about the three techniques. First approach is joint CTC approach, which is applied to speech translation, and then we can somehow stabilize the length problem. Second approach is try to use the searchable ASR intermediate so that we can have a direct benefit of the ASR improvement to speech translation thanks to the explainable the architecture of the clear division of the ASR and speech translation. And the third one is the operation sequence based on the speech translation generation. We can actually almost simultaneously recognize and translate the ASR and speech recognition result by keeping the alignment information. So we are also working on putting them to ESP.NET right now. So if you guys are interested in that, let's work together for this exciting, controllable, and explainable end-to-end speech translation paradigm. Thank you so much.
Thank you, Shinji. Very nice presentation and very, very interesting topics. Thank you so much.
Thank you.
So, questions. Do we have any questions? I have several, but I want to give the floor to the audience.
Maybe one question about the last part.
Sure.
Why, if I'm correct, the performance is even slightly better with the explainable approach compared to the direct speech translation. So why is that? Do you have any explanation for that?
Yes, slightly better. Yes, this is because this is we kind of putting this autoregressive manner so that this one is actually to try to estimate if we also first, for example, conditioned on the previous ASR result. And the same for the all other kind of other target token, we actually have an explicit the token dependency in the ASR part, so that we are expecting that this kind of form may actually improve the performance and so on. Is that clear?
Yeah, it's clear. But I assume that maybe it's a bit slower because you decode longer sequences.
Correct. This is actually one of the tuning part we have to do, and also training is actually a little bit slow. So yes, I mentioned that it's just slowing it, but since the translation, compared with the original translation result, the length becomes 3 times longer. So of course, still compared with the input, it is actually sometimes shorter or it's same length, but the training cost is actually higher. And also inference part, yes, it is longer, which means that we have more steps. So it takes actually time, but still it's not very high, because decoders the computation cost is generally not very high.
Hi, this is Evgeny. I want to thank you for a very interesting talk, and maybe also a question to the third part. So how do you represent these tuples with 3 elements? Does it, it's related to the previous question about the speed, but basically how do you represent? Is it also based on subwords, or you mix them somehow? Or?
Very good question. Yes, we actually using a BP. Yeah. Once we make this tuple, we can just making it as a long sequence. And of course, in the position part, we make it as a special token. And the others are we just using the subword, so that we can make it shorter. Yeah. But actually, this the operation part is sometimes making it very long. So that we actually also try to kind of summarize, even try to use the BPA in this kind of the shift part as well. But anyway, yeah, we're using the BPA to also try to make it shorter.
Okay. So potentially it's not even guaranteed that you will not get, let's say, 2 English words, and only then you get a 3rd or 4th German word, let's say. Yes. So it's that for each English word you actually get a translation of some kind.
Oh yeah, it is actually considered. Yes, it's just in this case is the same length, but the case that I don't have a corresponding there. The source the word does not corresponding to have the target word, and vice versa is also considered.
Okay. And maybe one last thing. So we did a few years ago, we also experimented with this OSM model, but on text input at that time, we actually tried to publish a paper, and it was basically a negative result, kind of going against the Felix Stahlberg paper, saying, okay, we cannot be better than just translation for text input, for just normal English input to these OSM sequences. So I was wondering whether you also repeated such an experiment, just checking whether the base quality on text input is also good or not.
We actually didn't try that. This is a very good suggestion. We will definitely do that. But we used to say that our experience, we actually had a difficulty of getting the similar result to this one. We actually needed to, yeah, it's actually related to my first the talk. We actually especially had to care about the length. In this case, the result, we didn't use CTC, by the way. So we actually had to carefully tune, handle the length. Otherwise, since as Rohan mentioned, it's actually 3 times longer. So it's actually requires more tuning to get to the reasonable result. But in our experience, after the tuning, we get this kind of a reasonable result. But yes, this is a very good the suggestion that we may also revisit the MT, the operation sequence. Yes.
Thanks.
Other questions?
Hi, may I have one last question?
Sure.
Thanks, Shinji, for the talk. I'm Marco. I just wanted to ask regarding the first part for the length control. My understanding was that including the CTC, in the CTC joint attention decoding mechanism, the blue score basically doesn't degrade, but also the length is kept very similar. So we can't enforce in this way to have very short translation. So I was just wondering whether my understanding is correct.
Yes,
And in this...
Exactly correct. This is, the length becomes robust to the kind of input source. In this sense, it is controllable, but probably the more controllable method will be that we can change the length, but we do not have so much degradation, right? Unfortunately, we cannot make this kind of the achievement in this approach, because anyway, CTC is trying to make some hard alignment so that we cannot have so much kind of the flexibility for the control of the length. So it can producing the how to say reasonable length of the result from the source, the sentence. However, it is not reasonable to fully control the length and also making it to be robust. Yeah, I would say controllable, but it means that it's robustly controlling without tuning the parameter. Yeah.
Thank you very much for the clarification. And one last question regarding this. I was wondering if you could give us some insights about the computational cost of this joint CTC decoding. How much is the overhead in terms of computational costs with respect to the plain beam search decoding? Thanks.
Yeah. Actually, this is not so high, I would say, because we also using it a lot for the even ASR side, and we can also make it the use for the streaming cases. I would say that the CTC part is a little bit tricky, especially when we're using the label synchronous, output synchronous decoding, which is the defaultly we're using in the ASR. But actually, we also recently working on the time synchronous decoding version of these approaches. In this case, actually, the computational cost is not so large. Anyway, my answer is that it's, for example, decoder computation part, just the likelihood, the score computation part for each output token position can become double or something like that. But entire decoding, the computational cost would not be very large, like 10% or something like that.
Okay, thank you very much, and thank you again for your talk. Thank you.
Thank you. Thank you for your question.
Can I have another question?
Sure.
Yeah, I was wondering, is the joint CTC attention impose some kind of constraint on the output vocabulary? Does it have to be characters, for instance?
There's no. Actually, we usually using the same token with the attention side. Yeah, there is no kind of constraint. Or I say that constraint would be that if we try to make this kind of the decoding algorithm simple, we should use the same the BP token as attention the decoder.
Yes, so we have to use the same, right? Same vocabulary.
Yeah, there is one technique. Actually, we could actually using the character for the CTC part, and then we can use the kind of the BP token, and then using some the tree technique to converting it. It is not very kind of it's not so complicated, and also getting the kind of almost similar the algorithm in terms of the computational cost. But the more general case of the different the BP token would be, I guess, a little bit difficult.
I was asking because in ASR, CTC is generally used with characters as the output. So I was wondering if, so in this experiment you report here, is it character or BP?
BP token, yeah, or BP token.
Okay.
I have a question on the last part.
Yes.
So are there any turnarounds or the tricks to handle the many-to-one or one-to-many and narrow alignments between the source and target languages in this kind of technology? Because there's a difficult problem to make it make it a sequence with the one using this kind of one-to-one alignment, I think.
Actually, this the original operation sequence already have such kind of the treatment. So apologize that this example, I should have provided such kind of example, but generally this part is not so difficult. However, the difficulty comes from, for example, the getting the good alignment, and especially when we using some other language, like for example Japanese and so on, we also need to use some kind of a tokenization and then throw it to the aligner and so on. Actually, this the data preparation part is yes, this work is almost data preparation, I would say, but this data preparation part is actually a little bit tricky, and we need to do some of the kind of knowledge of the text, the information of the source or target language to make the alignment. But after that, we don't need it, and yeah, many-to-many is basically actually considered in this kind of framework.
Okay, thank you. I got it. So another question, related question, is this kind of operation sequence model. It's not really difficult. It's really I think it's really difficult in a streaming situation because we don't have the whole input context to make this kind of operation sequence. So it may so how say. So in streaming situation, we don't have enough information to estimate the structure of the output sequence provided by this kind of operation sequence. So, did you find any results with the streaming conditions, not just for the offline conditions?
Yes, actually, this result is left side is offline and the right side is streaming. As you mentioned, actually, from the offline to the streaming, already all the method performance dropped. Yes, you are right that we cannot, further, we cannot get the entire sentence structure to the output, the sequence. So due to that, the performance is dropped. However, the important part is that this performance drop is not very large. And still, this method is comparable to the normal streaming speech translation. And then we can also get the reasonable kind of alignment result at the same time. So again, this kind of the demonstration is showing that as soon as ASR result is we can have a corresponding translation result. That is a kind of a unique property compared with the other speech translation based approach. I would say always having some kind of alignment information. I also want to add one more comment about the online, offline versus streaming approaches. One comment is that what kind of streaming techniques we are using. We are using a blockwise approach. We're just using the 320 millisecond as a block, the block size, and then shifting, and then connecting the ASR or even speech translation output. This is the more like a ASR side of the work, but we actually have some of the work related to the level synchronous blockwise beam search approaches. We developed in ASR, and we actually just using this technique for speech translation.
Okay, thank you very much. So all the techniques are really all the techniques applies to me. Thank you.
Okay. Yeah. Cool.
So any other questions for Shinji? I have one. I have other, but it's been already taken by the other. So when you talk about the rover approach in the second chapter of your presentation, if I understood well, you pass to the second decoder or to the MT, the output of the ASR, not the transcript, but the hidden state of the ASR decoder. So it's not clear to me how rover can impact on this, because rover, if I remember well, you apply it outside the decoding part. You apply
exactly.
So it's not clear to me how it can be used.
Yes, actually, after we have several, for example, ASR output, the different systems and so on, right? And then we actually are concatenating this result. Sorry, not concatenating, fusion. Using this result based on rover, right? This is completely offline process.
Okay.
And then given this kind of ASR output, and then we actually throw it to this part, and then generating the decoder state.
Oh, so okay, like a force decoding, like kind of force decoding or something like
that.
Exactly.
Yeah. So by doing that, we can actually making the benefit of the rover like fusion to the end-to-end system as well. Yeah.
Yeah, but the whole system. Well, now I don't want to enter in what is end-to-end and what is not end-to-end.
Yes, but exactly.
This is it still end-to-end? Because if you have
it's more like
okay.
It's more like, for example, we using the external resource. We use the language model shadow fusion as well.
Yeah, but there
this approach, yes,
you run the force decoding, so you generate. So you have an intermediate representation. Intermediate representation there is the output of the rover. But anyway, the technology is very interesting. So I don't want to start here to say what is end-to-end, what end-to-end. Okay.
Yes, yes.
No, but it was just because I didn't understand how rover can impact on the output of the of the ASR decoder. Okay.
Yeah.
So, any other question from the audience?
Yeah, I have one question.
Please, Juan.
For the next slide about the objective function. So there will be 3 parts, and according to my understanding, so you will need a triplet of data, right? You need audio, the transcription, and the translation, right?
Yeah, this case is we need the ASR transcription and translation at the same time. But of course, this method is actually keeping the original ASR and the MT structure, so that we actually first pre-train ASR model or MT the model based on the corresponding the training data, and then combine it and then fine-tuning it based on the both ASR and the translation result.
Okay, that makes sense.
So the final last question. Okay, so no questions. So thanks a lot. Let's thank the speaker again. Thanks, Shinji, for the nice presentation. And thanks everyone for being here today at the seminar. So just conclude, just to inform that we are looking for new speakers. So as you see, it's a very informal environment. If you want to support this activity, please just write it down me an email, and I will be very happy to find the schedule for the next seminar. Thanks a lot, everyone. Thanks a lot, Shinji, for the great presentation. Thank you.